All right, hello geometry students. Here's your 2.5 part 2 or 2.5b video for today, where our goal is similar to the last one, but we're going to use reasoning to prove statements in geometry. All right, so we're kind of combining algebra and geometry, but we're mostly going to be proving things in geometry here. So make sure you have that goal written down. Um, we are going to, let's just quick review some of the properties that we've learned, because properties are going to be used a lot in proofs. So here are the first ones. Just to recap, we have all four of these addition, subtraction, multiplication, and division properties of equality. That's where you could add something to both sides without changing the balance of the equation. You can subtract the same thing from both sides, you can multiply the same thing from both sides, or you can divide the same thing on both sides. After that, we also learned the three reflexive, symmetric, and transitive properties of equality. When you think of reflexive, think of A equals A. If we're talking, well, we'll get to that in a second. So A equals A, something is equal to itself. Symmetric is that sort of reflective idea. So if A equals B, then we can say that B equals A. And then the transitive is similar to our law of syllogism that we did the other day, but if A equals B and B equals C, then we can conclude that A also equals C. Our last one here was the substitution property, where if we know A is equal to B, then B can replace A in any expressions, or A can replace B. We also talked about the distributive property a little bit. We may or may not be using that today. Then there's the three properties of congruence, very similar to three of the properties of equality, where we still have the reflexive, symmetric, and transitive. But the reflexive is dealing with congruence, so congruence of segments or congruence of angles. Just an angle or segment is congruent to itself. You'll see instances when we will definitely use that. The symmetric property, if AB is equal to CD, congruent to CD, and this should be, these really should have segments over them. Then segment CD is congruent to segment AB. Same thing works with angles. And then the transitive property, if segment AB is congruent to segment CD, and segment CD is congruent to segment EF, then segment AB is congruent to segment EF. Same thing works with angles. We're just using A and B, B and C, and then A and C. And you can do the same thing here if they're both, if one of them is back. So if angle B is congruent to angle A, and angle B is congruent to angle C, then angle A is congruent to angle C. So this we talked about a little bit. So this will work for angles for right now. If the angles are congruent, if B is congruent to A and angle B is congruent to C, then angle A is congruent to C. So we'll be able to use that now. We did go through, I think we went through in the video last time, this one proof. So just to recap, when we're talking about all the different things we can use to reason here, we're going to use those properties. That's what we need to use to give our reasoning. So left side is always a statement and to help us prove what we're trying to prove. The right side is always the reason for why we can state that thing. So we're starting with x over 3 plus 4 equals 1. And the first thing you'll always put is the given, and that is our given. This thing right here is what we're given, so our reason is going to be given, and that's what we're going to state. Now, the next step, I think you hopefully remember you would subtract 4 from both sides, so you just have x equals over 3, and then if you subtract 4 from 1, that would cancel out, and then you have negative 3 over here. And that would be the subtraction property of equality. And then the last step would be to multiply both sides by 3. You get x equals negative 9. That would be the multiplication property of equality. So that's a basic algebraic proof, just using those properties as reasoning for getting from our what we start with to what we wanted to end with. Now we're going to do some more geometry ones, and these are still different things that we can use for reasoning, for giving reasoning for our statements. Um, the first bunch here is all of the properties of equality and congruence that we just talked about. Those are all usable. I want to also mention that the two postulates that we talked about are also usable. And I actually want to take this. Oops. I'll put this down here. Since that's another definition, I kind of wanted to make that go with these definitions over here. All right, so now we have those two postulates. This right here is one theorem that we actually haven't learned yet. We're going to do that in the next section. That all vertical angles are congruent. So a pair of vertical angles would be congruent. I don't know that we'll need that today, but I threw that in there. There's also a couple other theorems that we're going to add to this list of possible reasonings. And this list is just going to keep building and building all year with more and more theorems, more and more postulates. So these basic ones you're going to have to get used to and kind of have memorized just as things that you can use as reasonings, common reasonings and proofs. And then here's a bunch of definitions that I mentioned. The definition of congruence. So if two things are congruent, then their measures are also equal. Definition of midpoint, knowing that the point that is in the middle of a segment would bisect the segment, so the two segments that it cuts in half would be congruent. That's part of the definition of midpoint. Definition of complementary and supplementary angles, and then of linear pair. So remember, linear pair is two adjacent angles right next to each other that would form a straight angle. So they'd be supplementary. That comes straight from the definition of a linear pair. So that's basically what we're going to do for this rest of this time is we're going to go through, I think, 4 proofs. That is it. 4 proofs, so I want you to follow along. If you can, pause it and try to figure out the proof on your own first, but then I'll go through it with you. So this first one, we're given this picture over to the right. And again, typically you'll be given a picture. You'll be given this form, and you can use the format with the statements on the left, the reasons on the right. So these are all of our reasons. And you always start with the given. So right in this example right here, I already gave you all 5 steps. You just have to give the reasons for it. So let's start with EI equals RC. And you know what? I think there's actually a proof just like this on your test for this chapter. So I'll get used to this one. So we can say that EI, this part right here, is congruent to RC. So this whole part right here. Those are congruent. That's our given. So that should be the easy one to give a reason for. Then we're going to say that ER plus RI equals EI. ER plus RI is equal to the whole EI. And that actually comes straight from, and then we also have that RI plus IC would make up RC right here. That comes straight from the segment addition postulate. So just think about what is happening, that we're just adding the segments to make the whole thing. And chances are you'll be able to figure out where that comes from. That is a segment addition postulate. So that's one of our reasons here. Segment addition postulate. All right, then we're going to say that RI plus IC is equal to EI. How can we say that? RI plus IC is equal to EI. Well, it's because up here we already said that EI is congruent to RC. So if we know that those are congruent, then we can say that we can substitute this if they're congruent, we can replace these two. So we can say that that's equal to that, or really we're replacing the EI with the RC. So that would be substitution, you could say. All right. Now we're saying that ER plus RI equals RI plus IC. So this is now where, since we know that these two are equal, we're doing a little bit more substitution. Now we're substituting this part in for the, actually for the RC or the EI, however we replace it. That would also be substitution. If you would like to make that one step, I don't even know if it's spelled correctly. I always spell that wrong. Substitution. Now, if you want to make this into one step right here, from here to here, you could. Because you could say that since these two are equal, you can then say that these two would be equal by substitution. And then somehow we end up with ER here equaling IC. If you like, both sides have RI in common, so we subtracted RI from both sides. That would be the subtraction property of equality. And that's what we wanted to get to. So we got to our proof, what we're trying to prove, so give ourselves a smiley face. All right, maybe this seems totally foreign to you. Maybe this seems totally makes sense to you. Either way, we're going to be doing lots and lots more proofs. So don't be concerned right now. Just take it in, try to figure out where we got those reasonings from and how this process worked. Because we're going to start doing some without being given the statements. We're just going to fill it all in together. All right, we'll practice this more and more. So now we have a new one. We have our picture to the right, and we're given that we have segment AD. That's all we're given. So step one, we are given segment AD. Oops, AD. That is our given. I don't know why it does that. All right, we're trying to prove that segment AD is congruent to all three of these parts. So let's see, number 2, what can we say here? Now, one thing I want you to know is that not every proof is going to be done the same way. Like, I might do this differently than you might do this. As long as you do it legally and you reach the correct conclusion, it doesn't really matter the exact steps that you do it. So I'm just starting off with AB. I'm just trying something based on what I have for the picture. AB plus BC will make up AC. So that makes sense to me. And that's just a segment addition postulate. So remember, the segment addition postulate does not say that you can add 3 different things to make the segment. It's just 2 parts to make a segment. So I'm just going to take this one step at a time here and say that AB plus BC would be CD. Or sorry, it would be AC. Let's say that AC plus CD will get you the whole entire AD. That again would be the segment addition postulate. Oh, look, we have what AC is equal to. So why don't we substitute what AC is equal to in for AC? So my next step is going to be that AB plus BC plus CD is equal to AD by substitution. Technically, that's a substitution property of equality. All right. And, oh, actually, we're almost done here. Then the last step we just have to do is switch these around. So we have to say that AD is equal to AB plus BC plus CD. And we can flip those around because that would be the symmetric. This is 2, this is 3, this is 4, we'll do step 5. The symmetric property of equality, right? So we did the symmetric property of equality, but it was right there. It's not the transitive, and it's not the, oh, we're missing the reflexive in here. Weird. But anyway, I think we got to what we needed to get to. So I'm going to give myself a big smiley face. We got to the result using just our reasoning, what we have, what we know, and giving reasoning for it. So that'd be the second proof that we're doing. Third proof then. All right, we've got two different segments. We've got segment A, B, or well, AC and XZ here. And we're given a couple things. So our first step, we're given that segment AB is congruent to segment XY. So we can make a dash here because those are congruent. We also have that segment BC congruent to segment YZ. All right, so BC, we'll do two dashes because that's congruent to this. That is our given. We are now trying to prove that segment AC is congruent to segment XZ. So, well, we have segment AB plus segment BC be congruent to segment AC, and segment XY, and I'm not sure yet if I can use this, but this is something that we know. Segment YZ would be congruent to segment XZ, and that would both be the segment addition postulate again. Okay, now let's see if we can. Well, we could plug some things in here. So since AB is congruent to XY, let's plug in AB for XY. So segment AB, and let's do plus segment BC. We're going to plug both of those in here, and that would be congruent to segment XZ. That's just substitution. Because of what we were given, that would be substitution. Now, if ABC is congruent to AC and ABC, oh sorry, it's AB plus BC is congruent to AC, and AB plus BC is congruent to XZ, then we can do some substituting here and get that AC is congruent to XZ. We could say that would be substitution. We could also argue that that would be the transitive property of congruence. We'll just write substitution right now, but I would accept either one. Because technically the substitution property is just of equality. We're going to make one of congruence right now. And we got to what we need to get to. Right? AC is congruent to XZ. Yippee! Okay, I have one more proof for you. Just one more. This last one, it looks like we're going to deal with some more segments, and with two segments crossing at the intersection point T. So first of all, what are we given? We're given that segment AE is congruent to segment KI, and we're given the T is the midpoint of AE and KI, those segments. That's what we're given. All right, let's see what else we can do. So segment AE is congruent to segment KI. We're trying to prove that segment TI is congruent to segment TE. All right, so, well, what do we know? We can talk about what we just came up with before. We're talking about segment addition postulates. We could do that. We could say that segment AT, um, let's say that AT plus TE will equal AE, and that KT plus TI will equal KI. So this part plus this part will make up KI, and this part plus this part will make up AE. Those are both segment addition postulates. All right. Let's go from there. Let's see if we can do anything. Well, let's. What else do we know about from the given? So AE is congruent. We could then say that. Well, we can say that this KT is congruent to TI if that's the midpoint. So that means that KT, let's say the distance is equal to TI. Well, technically we have to say that they are congruent first, and that segment AT is congruent to segment TE. Those are congruent because of the definition of midpoint. Okay, it's cutting that in half. Now then we can say that Ki, the lengths themselves, KT is congruent to, KT is congruent to TI, yep, or equal to TI, sorry, and AT is equal to TE, just because of the definition of congruence. All right, let's see where we're at here. We haven't gotten to TI equals to TE yet. Well, you know what? I don't know if we needed to state that at all, because look at step 2 and step 1. So if we know that AE is congruent to KI, and we have AE and KI, why don't we just substitute in and say that these two right here are equal to each other? So that's, if that's equal to that and that's equal to that, and these two things are equal, it's kind of the transitive property. Technically it's substitution right now, but AT plus TE is then equal to KT plus TI. Since we know that these two are equal, and whatever they're equal to are going to be equal to each other, so that would, we'll say that's substitution. And there's really only one more step. Well, maybe 2 steps. We need to substitute for either AT or KT. Hold on here, let me think. Alright, I've got it. We did need this step 4. So if KT is equal to TI, let's substitute in KT for TI. So we're going to say this is KT here. And we're going to substitute TE for, oh no, we don't want KT in there for TI. We want TI in there for KT. So we're going to do, instead of KT, we're going to use TI. Since we can do that right here. And then instead of AT, we're going to use TE. This is a long proof, but we're almost there. And that would be step 6 by substitution again. Okay. Well, come on, just stay there. 7. We have 2TE equal to 2TI. Just by adding those together, that would be segment addition, I guess, or just simplifying things. And so I'm not going to give a reason to that one. But t equals te would be 2te. That's just simple addition. And then we can divide both sides by 2. That would be the division property of equality. I think that's what we needed to get to. Te is equal to ti. Uh-oh, we need to get to ti equals te. So one more step. Flip them around. Ti equals te. That would be the symmetric property of equality. Now we get the smiley face because we got to what we needed to conclude. Now if you look all in there, that was 9 steps. There might have been a way to get it in less steps, but you do need most of this information in here to get to what you have to prove that ti equals te. It takes a while, and you got to know your properties, you got to know your postulates, you got to know your definitions here because we use them all. Okay, so take that all in. Assess yourself on how you're feeling about these proofs and whatnot, and do your best with the practice that you're going to get now for doing some more proofs. All right. Make sure you're using these different reasonings to help you prove things. All right. So there you go. Use reasoning to prove statements in geometry. I'll talk to you later.